Here in section 11.11, we're going to be focusing on Taylor polynomials as a way of approximating a function, and therefore some uses of that in practice. So the first thing is to remind ourselves what the nth degree Taylor polynomial of a function f centered at a looks like. And remember, it's just going to be the first terms of the Taylor series up to the nth degree term. So the first term starts with f of a, and then we have f prime of a over 1 factorial times x minus a. And then continuing that pattern, we have the second derivative at a over 2 factorial times x minus a squared. The third degree term would be the third derivative at a over 3 factorial times x minus a cubed. And supposing we were continuing there up to the nth degree term, which would be the nth derivative at a over n factorial times x minus a to the power of n. Okay, so that gives us an nth degree polynomial, and we saw previously that the function x can be approximated by the nth degree Taylor polynomial for values of x that are close to a. We saw that in general the limit as n goes to infinity of Tn will converge to the function values of f of x, given that the Taylor polynomial Tn is an accurate representation of the function values of f. So in general, the Taylor polynomial is going to be a way to approximate a function. And how good of an approximation is it is a question that we might want to think about. So here are some natural questions that may arise when we're using a Taylor polynomial to approximate a function. So how good of an approximation is it? And by that we mean essentially what is the error in the approximation? So a question would be, how large is how large is the error? And how large should we take n to in order to achieve a desired accuracy? So then the question would be, then, if I want my error to be within a certain value, I don't want my error to be too big, so I give myself a restriction on how big I want my error to be. So then how large does n need to be to guarantee that my approximation is within this desired accuracy? So in other words, our goal there would be to find n such that the error is less than some desired value. Okay? And so both of these questions involve the error, so we need to consider the remainder, Rn, which is essentially the difference between the function and its approximation Tn. Okay, so we know that in general we can think about Rn in a couple of different ways. For instance, I can directly compare the functions f of x and Tn of x, and then consider their graphs. So here in the first method for estimating the error, we can just compare the graphs of f of x and Tn of x together, and then that will essentially tell us something about Rn of x. And so by observing how those two graphs compare, we can observe essentially where they begin to go apart from one another. Okay? So the idea is that the graph of f of x and the graph of Tn of x should be close to each other in a particular range around the center A. But if we go further away from A, then the two graphs are going to begin to diverge from one another. And so the question is, how close to A do we need to be within a desired error? So that's one way. Another way is to use the alternating series estimation theorem. And if you remember, what this says is that if I have an alternating series, I could get a bound on the error by looking at the n plus 1th term. So remember, it says something that Rn is less than or equal to Bn plus 1. I should say in absolute values. So that's going to be one other approach, is because oftentimes we get a Taylor series that is an alternating series. And so thinking of it as an alternating series, you can use the alternating series estimation theorem. And then a third possibility is to use Taylor's inequality. And that also gives us a similar way of getting a bound on Rn using the n plus 1th derivative. If we know something about how large the n plus 1th derivative could be, we can then get a bound on the error in the approximation. Okay, so let's think about this with a specific example. Suppose I want to approximate the function f of x equals the cube root of x with a Taylor polynomial of degree 2 centered at a equals 8. Okay, so let's start with that part, and then we can think about the second part, which is to think about how accurate that approximation truly is. So let's write out what our Taylor approximation T2 will look like, since we're doing a degree 2 polynomial. It'll be f of 8 plus f prime of 8 times x minus 8 plus f double prime of 8 over 2 times x minus 8 squared. Okay, so notice that we'll need up to the second derivative evaluated at 8 for this particular f of x. So let's work those out up above here. So we know that given f of x is the cube root of x, I can write it as x to the 1/3 power. So we have f of 8, of course, is just the cube root of 8, 2. F prime of x will be 1 over 3 x to the negative 2 over 3. And so here I can evaluate f prime of 8 as 1 over 3 times 8 to the 2/3 power. 8 to the 2/3 power will be the cube root of 8 squared, so it'll be 4 squared. I'm sorry, it'll be 2 squared, which is 4. So it'll be 1 over 3 times 4 is 12. And then the second derivative, we'll get negative 2 over 9 x to the negative 5 over 3. And so the second derivative at 8 will be negative 2 over 9 times 8 to the 5/3. So again, here we're taking the cube root of 8 and then raising it to a power of 5. So I think that'll be 2 to the power of 5, which is 32. And then I think reducing here, 2 into 32 is 16. And then 9 times 16 gives me 144 in the denominator. Now let's put those values into T2. So here our second order Taylor polynomial will be f of 8, which was 2, plus f prime of 8, which was 1 over 12, times x minus 8, plus f double prime of 8, which was minus 1 over 144, over 2, x minus 8 squared. So here let's simplify that last coefficient there. So it'll be 2 plus 1 over 12 x minus 8, and then this one simplifies to minus 1 over 2 times 144, so 1 over 288 x minus 8 squared. Okay. So here is our second order Taylor polynomial. And it's approximating the cube root function. And so the question is now, if I were to put a value of x into this polynomial that's within a distance of 1 away from 8, in other words, it's in the range from 7 to 9, what can we say about how accurate this approximation is? Okay, so notice that we do not have a alternating series, so I can't use the alternating series estimation theorem. So unfortunately, that option is not available. However, I can just use Taylor's theorem. So let's think about how Taylor's theorem might tell us something about the error in Rn. So in this case, we'll do R3. No, sorry. Sorry, take that back. I want R2, since we're doing T2. And we know this will be less than or equal to m over 3 factorial times the absolute value of x minus 8 to the power of 3, where m is an upper bound of the third derivative for x in this particular range here. Okay, so let's actually do one more derivative. We've already done up to the second derivative, so I'm going to compute one more derivative here to see how we can get a value for m. So let's see, the third derivative will have negative 2 over 9 multiplied by negative 5 over 3 gives me 10 over 27 x to the negative 8 over 3. Okay. So that's for my absolute value of, notice that taking the absolute value here doesn't change anything since we're on a range where x is positive. So another thing I notice is that this function is decreasing. It's a decreasing function. I notice that as x goes from 7 to 9, since it's decreasing, the biggest value occurs when x is 7, right? Because as x gets bigger, it decreases in size. So this will be less than or equal to 10 over 27 times 7 to the power of negative 8 over 3. And so to get an approximation of this value at this point, we're going to need to actually plug this into a calculator, which kind of actually, if we think about it, defeats the point of what we're doing here in the first place. But let's just do it anyway, because otherwise we might have a bound that is not as precise as we would like. Okay, so here evaluating 10 over 27 times 7 to the negative 8 over 3, I get something that is close to 0.0021. In fact, here we'll just use the less than symbol here. Okay. And so this will be a value that we can use for m, since we see here that the third derivative on this interval from 7 to 9 is going to be less than or equal to this value here, so this will be m. And so putting that all together here, well, we know that m we can use 0.0021 over 3 factorial. What can we say about the absolute value of x minus 8 cubed? Well, here we know that on the interval 7 to 9, x minus 8 will be between -1 and +1. So we can say here that the absolute value of x minus 8 is less than or equal to 1. So we know that this here will be less than or equal to 1 to the power of 3. And so this gives us our upper bound on the error, which here, if we do 0.0021 divided by 3 factorial, I get something on the order of 3.5 times 10 to the -4, or about 0.00035. Okay, so that shows here that R3, the error in this approximation, is less than or equal to 0.00035 for x in between 7 and 9. So in other words, as long as we're using Tn to approximate our function, in other words, using this degree 2 Taylor polynomial only for values of x in between 7 and 9, so pretty close, a distance of 1 away from 8. They're all very close to 8. As long as we're within that range here, the polynomial and the actual cube root function will not differ by more than this amount here. So that guarantees that our approximation with the Taylor polynomial will be relatively close to the actual value of the cube root.